All right, so any questions yet?
How was your day today?
My day's good, thank you. How about yours?
All right.
It's all right.
Is this your shorter day?
It's shorter than Monday, but it's longer than other days.
So it's an inequality deal?
Yeah, but I started off by going to the gym, so it was good.
Which means you got home and
Yes, or it's sunny, or it's not sunny. Yeah.
you already passed that class, okay?
Right. Flashback.
Once you think you're out, it's just...
Yeah. All right, so let's see. Logistics. So the daily class meets Monday through Friday. This class meets Monday and Wednesday. Even though this class technically goes until 2:05, on Mondays I have another class at 2, so it gets cut short. And on Wednesdays I'll probably end it around 2 at the latest. And so there's going to be a bit of synchronization issue. So what I'm doing is the same as last quarter. In 222 section A, the one before this, Friday's class I'm not going to lecture on new material. Okay, I will come in, and if there's questions I'll be happy to talk about those. If people are working on code and want to, show me what they're doing or have help debugging things like that, I'm happy to do that. But I'm not planning to go over additional material in there. So this section, right, if you're free Fridays at 11, right, you're welcome to come in for that. Along those lines, Monday is a holiday, so there's no class here Monday. So the next time we meet will be a week from today. So that's a little brutal because there's an assignment due next Friday, and this will happen week 7 also. So the Monday, Wednesdays get hit double whammied. There's a discussion area on Canvas that I'd like people to start thinking about taking better advantage of. Okay, you can go in and you can start a discussion, and what you post there everybody can see and people can comment on it, and I can see it. Okay, so if you're always welcome to email me. Okay, that's always a fine option. But if you're kind of like generally stuck, I'm not really sure I understand what we were supposed to do here, or hey, I'm trying to get to the server and it's not responding, do you know if it's down, right? Those are things you can post a discussion on Canvas and get some groupthink going. And I'll see those when they get posted, and if I feel like I can contribute to it, I'll go ahead and do that. But oftentimes, people will be answering questions for one another, and that's great. Okay, it's a different way to look at some of this stuff. It's a different version of explanations and so on and so forth. The one caveat is don't post working code. Okay, I finally got my code to work. Here's what it looks like. Okay, you don't want to do that because other people will see it, and you can't unsee code once you've seen it unless you go watch 3 hours of Gilligan's Island. So so don't post working code. But if your program is blowing up, right, I've got it isolated, this 5 lines of code, and for some reason it seg faults when I run this, go ahead and post that, right? Let other people look at it. And my suggestion would be, don't, if somebody does that, don't just say, oh, do it like this instead, right? But chances are somebody else had a similar issue, and maybe they did some print statement somewhere, or they did something in GDB and it helped them figure out what the problem was, and maybe they would post that in the discussion and say, hey, try doing this and see what happens, and see if that tells you where the error is. So let it be a resource that's available for you to use. And more of this course, if somebody sends me a question that's not, directly related to you, not like I can't be in class next week, but something like I don't understand what the init function is supposed to do in this case, right? Chances are I will go ahead and I'll start a discussion question and say, you know, I had some questions about what the init function does in this case. Here's what, you know, the answer is. So you can always start that directly yourself in Canvas. All right, everybody okay with ODP 201? That got turned in fine. I made several hiccups when I was posting it, but I finally got it figured out. It's a new posting system this quarter, so. But I think I've got the details worked out now. All right, so I want to talk about structures, in particular the struct statement in C. And I know you touch on this in 121, but possibly not in a lot of detail and possibly a long time in the past. So I want to refresh ourselves on what the struct statement is all about. So the basic idea is similar to an array. With an array of temperature readings, we've got an array called temp, and it's got 50 entries, and that represents what the temperature reading was every 10 minutes, for example. Now we could just as easily have 50 variables called temperature 1, temperature 2, temperature 3, and so on. But then if we wanted to print this out with a print routine, we have to call our print routine and pass it 50 variables, right? So gathering those together into a single array called temperature lets us treat this whole set of 50 pieces of data as a single thing. And once we pass that thing to a function, it can get to all of those 50 pieces of data inside. In the case of an array, by saying temperature bracket, whatever index we want. Similar idea with a structure. So suppose we have a program that's processing information about students, and we want to know the student's name, their student ID, and the GPA. We could have 3 variables, name, GPA, and student ID. And if we want an array of 1,000 students, we could just have 3 arrays, an array of names, an array of student IDs, and an array of GPAs. And we use those together. So kind of like the word index program from 224. A structure lets us gather those 3 pieces of data and treat them as a single thing. So that's the motivation. So syntax-wise, we use the keyword struct, followed by the name of our structure. So let's say we're going to call this student. And we're defining for the compiler this new type of variable called a struct student. So we put a curly brace, start the definition, and now we just list all the different variables that are going to be associated with a student. So maybe there's a character star name, and an integer student ID, and a double GPA. And a closing curly brace, and then a semicolon. And our structure might have just 2 or 3 things to it, or it might have 100 things. It might have structures inside itself. It might have arrays. It might have arrays of structures. It could be arbitrarily complex, but the structure of the statement is the same. Struct, name of structure, curly braces, and closing, all the different fields associated with that. So these things are called fields.
There's a semicolon at the end of it?
Mm-hmm. You don't remember that?
No.
Usually there's a variable name and then a semicolon. But like
yeah,
this, there's got to be a
yeah.
semicolon. All right, so this structure has 3 fields, name, student ID, and GPA. So this defines a structure, but it hasn't actually created a variable yet. So if you want to make a variable that contains a struct student, you do it exactly like any other variable declaration. instead of saying integer x or character x, we could say struct student x. So let's make a struct student S1. And I'm going to make a pair of these. I'll make 3 of them for no particular reason. Struct student S1, S2, S3. So the way to think of this is I've got 3 students now in my program. All right, this struct statement, this usually goes in the beginning of your file outside of main. There's a scoping here. We want this to be global, basically. So typically we would write this, and then we would start our main program. And if we're making a function in a separate file, we would need to define what a struct student is. So we'd put that in the beginning of the file, and then we'd start the definition of our function. And any file where we want to use a struct student, we need this set of code to define what a struct student is. So typically, this is something you'd put in a .h file, and you would just include it. You don't have to do that. You can type this into every file that you have. But if you put it into .h and it changes, you only have to change it in the .h file. And since you include that in all your other files, that change gets carried through everywhere. And if you look at stdio.h, it's filled with a whole bunch of structure definitions.
So would you just put that in the .h file, or you would put the struct student S1 to include?
If I wanted this line of code to be part of every file, for some reason, then I would put it in the .h. But generally not. This is usually going to go inside main. If I wanted it to be global, I'd put it outside main, but we don't usually do globals. But again, you don't have to do that. It's just something to keep in mind, right? It can simplify your life down the road. All right, so we've defined what a struct student is, and we've defined 3 variables, each of which is a struct student. How do we actually use one of these variables? You write the variable name followed by a period, followed by the name of the field. So if I say s1.name, that's the name field of this student S1. And so I can say something like s1.gpa equals 3.5. And I could say s2.gpa equals 4.0. And those are totally different variables, right? This is the GPA field within this variable S2. This is the GPA field within this variable S1. They're totally separate. They're in different locations in memory. So S1 is like a super variable, and it's got these different pieces to it that we can get to. That's all that's going on with a structure. And we'll see this a lot in 223 when we're working with object-oriented languages like Java. This is how we get to the different pieces of an object. So this is a notion that will carry over in Spring. All right, pretty straightforward. So if you want, you can have an array of these things. So there's an array of 1,000 students, and it's named all. And if I want to get to the student ID of student 5, I could say all bracket 5 dot student ID. And now whatever student is stored at index 5, this refers to that student's student ID.
So
each of these structures are acting as kind of an array where the student ID is going to be put after the name, and the GPA is put after the student ID of memory, right?
Possibly, but possibly not. The upside to that answer is it does not affect you, right? Because you access the student ID by saying .sid, it doesn't really matter where it's stored. But depending on the compiler, it could decide to store the student ID and GPA first, and then store the name. There might be some reason the compiler prefers to do that. And it will often leave space in between things. So if my name is only, if I had a character array of length 2, and that was stored in the first 2 locations in memory for my structure, and then I have an integer, it's not going to store the integer right here. It's going to leave some space. So your GDB quiz lets you explore that in the debugger. Oh, I fixed the quizzes so you can do them multiple times. So hopefully, yay. All right, so we have arrays of structures. And as with all this stuff, it looks pretty much like an array of any other type of variable. I am really lagging with these uploads, but that's okay. Yeah, like I said. All right, well, how do we pass structures to subroutines, functions, just like any other variable? So I could have a void function called fun, and I could say, give me a struct student called x. And somewhere in here I might say something like x.gpa equals this is the b function. Just adjust someone's GPA to 3. So in my main program or in some other function, I could do the following. Again, let's suppose S1 was a struct student. I could just say fun S1. And what happens, the system jumps to this set of code. It sets x equal to S1. And so when I say x.gpa, I'm actually operating on S1.gpa. Alright, so exactly the same as usual. But, as usual, if I make a change here to x, it's not going to actually change S1. Because we got the whole pass by value thing to deal with. So it's like passing an integer to a function, and that function we set the integer to 0. When we come out of the function, the integer we passed in hasn't changed. So we need to be a little careful of that. But we'll fix that up pretty quickly. All right, so far so good. So let's look at ODP 202. So this went live this morning. It's due at 8 o'clock tomorrow. So this is working with arrays of structure. So there's 2 pieces to this. The first piece is to define a structure named node that contains exactly 3 fields. So data, next, and valid. All of those are integers. So define a structure just like we did for student, right, with 3 fields and integers. And a general note here, these ODPs are partly an exercise in being able to follow a specification for a program. So if you decide to call data with an uppercase D, your code's not going to compile correctly when you try to link it to the test bed. Okay, or if you name your node something, your structure something other than node, if you call it my node, it's not going to work. So you really got to follow these pretty specifically. So structure named node containing 3 integer fields, data, next, and valid. That's your first task, right? Write the structure statement. Second task, make a function called init. Okay, put this in the file. I put it in a file called init.c, but you could put it in any file you want. And init.c is going to define the structure and then define a single function called init. So the prototype for init looks like this. It takes a pointer to a struct node. Okay, that's an array of struct nodes. And it returns void. I have no return value. So over here, if we did something like struct node mydata bracket 100, and then I tried to call init and pass it mydata inside init, it's going to see a struct node pointer. An array of structures is just like an array of anything else. It's a pointer. It's a pointer to the first element in that array. So this X that comes in here is going to be basically the address of mydata bracket 0. And inside init, if I say X bracket 5, that's going to refer to the same thing as mydata bracket 5. So remember, with arrays, if you pass an array to a function and you change one of the elements in that array, that change does carry back to the caller. All right, so your prototype for init is just accept a pointer to a struct node and return void. And the goal of init is twofold. For most of the elements, so you assume that this is an array of 100 elements, 100 struct nodes. For elements 1 through 99, set your valid data and next fields as shown. Okay, valid is 0, data is 999, and next is negative 5 nines. For element 0, you initialize that differently. Set the valid to 1, data to 42, and next to -1. And then return. So make a structure statement, make a function called init, takes a struct node pointer, set element 0 according to this, so just write 3 statements to set each of those 3 fields. And then make a for loop from 1 to 99, and inside that for loop, make 3 assignment statements to set each of those fields accordingly, and then just return. All right, write that up, make yourself a main program, and test it. Make sure it compiles. So in your main program, make an array of 100 struct nodes, and then pass it to your init function. And then look at the values of some of the fields. Print them out, maybe make a for loop and print them out. Maybe run it in GDB and use the print statement to actually look at the value of the fields inside that array. And convince yourself that it works. Usually if it doesn't work, it's going to segfault, so it'll be really clear. But test that, make sure that it works. Once you think that it's working, go ahead and assess it. So use the usual compile command to build your executable. So /temp/main.o is the test bed. I'm assuming init.c has your init function. Compile them together into an executable main, and then go ahead and assess. So assess main in the name of your source code. And there's one test to run, so it's an all or nothing. All right, yes? You can assume it's going to be passed an array of at least 100, so you can loop through to 100. Could be longer, but
so if you have a main function and an init function, then you have to declare the special node.
Yep. Which is where you can play around with the .h file if you want. Other questions on that? Yeah.
If we're using the header, do you want us to, I guess you don't have it set up for assess that should take a header file, so if we have issues with that, we just send it to you.
Yeah, so the downside of assess is it only takes a single source code file. I should just let it take more than one. Jam them all together.
You can just do it for log purposes.
Yeah, I'll do that. Cool. Version 3. All right, other questions? So let's keep talking about linked list, but let's use this language of this struct node. Okay, and this is leading us into PA1, and before we hit 2 o'clock today, we'll have talked about PA1, because I need you to know what you need to know before we leave class, since I won't see you for a week. So remember our setup. We were imagining an array. And we were storing some numbers in order, so let's just put some initial values in here. 2, 5, 8, 13, 21, 34. And we're going to think of this as so where we were Monday, right? We were trying to insert things into this list, and the idea was if we wanted to insert, say, a 6, the 6 had to go right here at location 2, and in order to do that without losing anything, we had to move all these things down, and that gave us a problem. And so the idea was we were going to insert the 6 down here, and we were no longer going to assume that our data was stored at location 0, followed by 1, followed by 2, followed by 3, followed by 4. We were going to allow things to move around in this array. So we needed, with each number, another number that told us the index of the next entry. So this is 2 of our fields. So we have a data field and a next field. And at this point, it looks like this, right? Our first number is always stored at element 0. We insert a 2, we have a 2 as our first number, followed by whatever is at index 1, which is a 5, followed by what's at index 2, which is an 8, followed by what's at index 3, which is a 13, followed by a 21, followed by a 34, and 34 is the end of our list. So we put a special flag in here, which was -1. Okay, and -1 means end of list. All right, so we want to insert a 6. And the idea was we would simply put that in the next open spot. We would take the node that came right before this, which was a 5, and now instead of having 5 point to the 8, we're going to change its next field to point to our new piece of data, which unfortunately happens to be index 6, but it's an index number. And we change this to point wherever the previous data was pointing, which was a 2. So we can go through our data in sorted order still very easily. 2 is followed by a 5, is followed by a 6, is followed by an 8, and so on. And it only cost us a few operations. Copy our number into here, change this next field, set this next field. Okay, now let's insert 15. So where's the 15 going to go? It's going to go at index 7. And we know that because we haven't written anything here in index 7 yet. That doesn't work for the computer though. Because in the computer there's no such thing as an empty memory location. We might not show a number here, but there is some number stored there. Probably some big, long, horrible number around -2 billion. But there's something there. And we can't just go through and look at the data field until we get to something that we recognize as being unused. Because we could have any possible number in here. So what we're going to do is we're going to introduce a third field, which is what we call valid. And valid is a simple flag. 1 means that that entry in the array is part of our list. And 0 means it's not. So right now, all of these are going to be 1s. And these are going to be 0s. So there's some values here, we don't know what they are, but we don't care because we're not looking here or here to find where to put in the next number. We're only looking at the valid fields. So what do? We start at the very beginning of the list and we check the valid bit on entry 0. And it's a 1, that entry is in use. Check the next valid bit. That's a 1, that's in use. Keep going until we get to a 0. That's a spot that's available in our array. So we're trying to insert a 15. We're going to put a 15 right here. We need to know what value comes right before this. Well, we're going to have to do that the long, painful way, which is simply start at the first number. There's a 2 followed by a 5, followed by a 6, followed by an 8, followed by a 13. All of those are less than 15. So we know 15 comes after that. But this is followed by a 21. That's bigger than 15. So we know the 15 comes right before a 21. We need to remember what the previous one was that we were looking at. Once we get to 21, we need to know how to back up one spot. The last node we looked at was 13. That's the one that we change its next field to. So we change that to point to the index of our new data, 7, and we change this to point wherever that previous node was pointing, which is a 4. So now that's part of our list. We need to do one more thing. Change the valid bit. Because if we don't, the next time we try to insert, we'll come through and we'll say, hey, this spot's available, and we'll overwrite our 15. All right, so now we've got a pretty genuine linked list sitting here. So what if we want to delete? So let's delete the 8. So start at the beginning of the list. Is this an 8? No. What's the next entry? It's a 5. Is that an 8? No. What's the next entry? It's down here is a 6. Is that an 8? No. What's the next entry? It's over here is an 8. Hey, that's an 8. That's what we want to delete. If we get to the end of the list and we haven't found our number, then we were asked to delete something that wasn't in there. In fact, if we find a number bigger than 8, we don't have to keep searching since the list is sorted. But in this case, we found the 8. It's sitting right here at location 2. We still need to know what the previous node was right before 8. That was this node right here, right? Value of 6, and it says the next field is 8. How do we change something to get rid of the 8?
Change this next value to what 8's next value?
Yep. Change this 2 to be whatever the deleted node was pointing to, in this case a 3. And that right there removes the 8 from the list. So follow it through, start at a 2, followed by a 5, followed by a 6, followed by 13. We skipped over the 8.
So now that we have the valid column, you change that to 0.
And change this to a 0. Because if we don't, we're not using that location in the array anymore, but nobody else is going to be able to use it either. Because when we're trying to insert, if there's a 1 in here, it's going to look like that's in use. That's a memory leak. In that case, after we stored 100 things in our array, we'd have no space left to store anything. Even if we had deleted 99 things, we'd be out of memory. So classic memory leak. So we set that to a 0. We're good to go for next time. Okay, let's insert. What should we insert? I don't know. Let's insert a 20. So first thing we're going to do is find out where we're going to put it in the array. So start at the beginning of the array, look for a valid bit. We're not following the list yet. We're just going through sequentially trying to find a 0 in a valid bit. That happens right here at index 2. So this is where we're going to put our 20. And now it's the same procedure as before. Start at the beginning of the list, work through it until you find a node right before where you want to insert, which in this case is 15. So 15 points to 21. So we want to insert it between this spot 15 and this spot 21. So take this spot before and change it to point to the index of the new piece of data. That's a 2. And set this to point wherever this was pointing, which is a 4. And set the valid bit to 1. Making sense? So the details of this may be murky at this point. That's okay. We're going to look at a different way of visualizing this, which is going to make this easier. And it's going to take some work. And as you write code to do this, that's going to help you understand what's going on also. But we're going to get away from the tabular notion in a minute.
So the ODP that we're working on, that's pretty much what this is, right?
The ODP you're working on is basically how you initialize this, because how do you create an empty list to begin with? Well, with this setup, we would just need to go through and set all the valid bits to 0. The init program does something slightly different with element 0, and we'll see why in a little bit. But yeah, that's basically going to be part of PA1. That'll initialize your linked list to be empty. So let's try one more. Let's insert a 50. So we'll go through looking for a valid bit of 0. We find one down here. We put our 50 there. Now we follow our nodes in our linked list and find where we should insert the 50. And we're going to follow all the way through to 34. And 34, we can't follow it anymore. That's the end of the list. So we're inserting right after 34. So what do? Change 34 to point to our new index, and have 50 point where the previous node was pointing. So it's the same algorithm, even though this is a flag instead of an actual index. And now we've got a list with all these pieces of data in there. And we have to change the valid bit. Thank you. question. Yes. If our array only had 9 slots in it, this would be full. We'd be out of memory. In PA1, your array is going to have 100 entries to it. So you can have up to 100 pieces of data in your list. And if you try to insert something more at this point, what I would need to do is, in my code, when I'm looking for a place to insert, I would say for I equals 0, I less than or equal to 8. Right? If the valid bit is 0, go ahead and return that index. If I come out of that for loop, I didn't find a spot that I could insert in, and there's no spots left, so I would have to do something to say, hey, we're out of memory. We can't insert anything more. Now, PA2 is going to be very much like PA1, except instead of using an array with these structures and these pointers to indexes and stuff, we're actually going to be using memory addresses. And we'll make nodes that actually contain data and an address in memory. And we'll be tinkering with the low-level memory mapping of our data. But PA1 lets you do that without getting into pointers and mallocs and frees and addresses and things that are pointed to by such and so on. So we're deferring the pointer stuff for another week. And then we'll jump into it in PA2. All right, well, let me give you a different way to look at what's going on here. So pictures are going to be your best friend when you're working on data structures, because code is very precise and it's very flavorful to a CPU, but it's not so good for us usually. You're going to write code and it's going to say this thing is equal to that and that thing is equal to this other thing, and if this thing's equal to that, then do something else. And you're going to be trying to do these kinds of manipulations that we've been doing, right? Change this thing to point to what the previous thing was pointing to. But trying to debug code like that is really frustrating for most people. So if you can draw a picture that captures what's going on, and then you can go through your code and update the picture, if you're doing something wrong in your code, it will jump out at you visually, right? And our visual processing is usually a lot better than our sequential processing or interpreting of C. So you're going to want a big whiteboard or big sheets of paper and a fine pencil with a good eraser to do this stuff. So let's draw some pictures. So here's 4 struct nodes. Okay, I'm drawing them with a rectangle. And I'm not going to worry about showing the valid field on here, because the valid field is just housekeeping. It's something that we use when we want to find a new node, space in our array to store a new node. We use that to know where we can store new data. So I'm not going to worry about the valid field. I'm really just showing the data and the next. So I'm supposing that I've stored 2, 5, 15, and 25 into our list. So we've got 4 of these struct nodes. The data values are set accordingly, and the next value I'm just going to draw an arrow. So in some way, I want this node to say, hey, this is the node that comes next. All right, PA1, we're going to store the index of this in the array. PA2, we're going to store the memory address of this. But I'm just going to draw an arrow like this. And node 5 is going to point to node 15, and 15 is going to point to 25. And 25 doesn't point anywhere. It's the end of the list. So I'm just going to write the word null down here to say there's nothing after this node. And that's a little cleaner than an arrow that just goes nowhere. So I'm just going to write the word null to say this doesn't point to anything. All right, well now let's see what some of our operations look like. So let's insert a 6. So what do? We create a new node. We set its data value to 6. We find the node right before it, and wherever that's pointing, we have 6 point there. And the node before it, instead of pointing where it was, points to our new node. Bang, we're done. So that's all of that, setting things equal to this and copying this down here. That's all we're trying to accomplish. Let me scribble this out. And you can start to envision an algorithm for doing this to insert the 6. Well, we would begin at the first node, and that's less than 6. So we would go on to the second node, that's less than 6. We'd go on to the third node, that's bigger than 6. So we would take the previous node before we moved on, that's the one that we do the changes to. Whatever that's pointing to, make this point there, and then have this point to our new node. It's a really simple algorithm once you understand it. But understanding it is one challenge, and then writing code for it is a whole different challenge. All right, let's delete something. Let's delete 15. Well, start here, there's a 2, that points here, that points here, that points to a 15. That's the node we want to delete. Go to the previous node and have that point wherever 15 is pointing. There's your deletion. Is it a problem that 2 things are pointing to 25? No. Is it a little weird? Sure. But stuff is pointing everywhere if we decide to interpret some location in memory as pointing to something else. Who knows where it's pointing, right? Now, in practice, we would do something to say that whatever memory is being used for this is available for other uses. And it might be used the next time that we create a node. It might be used by the operating system when it wants to do something we don't know or care. So these operations are pretty straightforward now, if you're thinking of this pictorially. Okay, the most important thing at this point is understanding this and finding a way to represent this that makes sense to you. It may not be exactly like this, it may be nothing like this, but it's probably not going to be a bunch of C statements, unless that's how you view the world. I've known a few people like that. I knew someone who actually dreamed in Fortran, an old programming language. But you want some way of this notion of data with pointers to other pieces of data and being able to modify it that makes sense to you so that you can work with algorithms for inserting and deleting and going through the list and finding where to insert. And as you go through, sort of keeping track of the previous and the current node so that you always know what the node was before. That's the biggest challenge right now. Right, is find a way to make peace with this. And it can take a while. Okay, when I first learned linked lists, it was really frustrating at first. Because I don't remember how my teacher did it. I don't think it was exactly like this, but there were all these weird edge cases that kept popping up and stuff. But at some point, you know, you wake up one morning and suddenly like, hey, this makes sense. So that's one thing. Nothing to do with code. Okay. If you don't have a good grasp of this, though, don't write code. Okay, don't even say VI. Because occasionally students will come to me with their program and they say, my insert function isn't working. And I'll say, okay, show me what it's doing. Oh, I don't understand the pictures, I just wrote the code. Well, it's really hard to debug. Right, because this is inherently something that has some kind of visual representation, right? So this will help. Find some way to do this, and it might be like this, it might be something different. But get into the habit of making pictures. right? Practice what the operations are. If you're trying to make an insert routine, how am I going to do that? And then start adding some variable names to this kind of thing, and then at some point start writing pseudocode, and then start writing C. Okay, but you really want to understand the problem before you jump into the coding. All right, don't worry if this is fuzzy right now, because this is new for most of us. So let me introduce one more wrinkle here, and then we'll go ahead and take a break, and then we'll talk PA1. So let's go back to our array for a minute. Let's suppose I want to delete the number 2. Well, I start off, and my first element in my array is the number I want to delete. So I have to find the node before it and have that point to location 1. Well, there is no node before it. It's the first element in our linked list. So how am I going to delete this? I know I can eventually change the valid bit to 0. But if I start looking at my data, I'm always looking at element 0. I'm always going to see that too. What I really need to do is somehow record the fact that my first element of my linked list is no longer at index 0, but it's actually at index 1. So that when I ask what's the data stored in my linked list, the first thing I see is a 5. And that's kind of a pain. It makes treatment of deleting the first node in a list special. It also makes special the case of having an empty list. Not in this case. We can handle that with an array. But when we're dealing with memory, an empty list is going to be fundamentally different from a list with 1 node, or 2 nodes, or 3 nodes. Because with all those other linked lists, we have at least a node that we can point to. With an empty list, we have nothing we can point to. So we're going to use a trick. And if the motivation for this isn't clear, that's okay. You can trust me. This will make your life easier. But as we start working with linked lists in memory instead of an array, it'll become more clear why doing what we're about to do is a simplification. So we're going to introduce what's called a sentinel node. And what's a sentinel? It's a node with no particular data value and a next field of null. It's a node that is always present. We never delete it. We never use it. We never look at its data value. We never insert anything before it. Its only purpose is to point to the first node of our linked list. But it actually is a node in a linked list. So it points to the first meaningful node in our linked list. So an empty list actually has 1 node, and its next field is set to null. But if we want a list containing 2 and 3 and 5, the setup is the same as before, but we still have this sentinel node in the beginning. And it points to our first actual node. So this is a list containing 3 pieces of data, 2, 3, and 5, even though it's got 4 nodes being used. This is a list that contains no data, even though it's got 1 node being used. So we always have this extra node. The advantage is this never gets deleted. And our actual data, we always have a node before the first node. If we want to insert something like a 1, we could simply take this, point to the 1, and then point up there. And so the algorithm for inserting in the beginning of the list, for deleting the beginning of the list, for deleting all the nodes of a list, for inserting into an empty list, our algorithms are always going to be the same. It gets rid of almost all the special cases. And like I say, that'll be more apparent when we're working with memory addresses directly instead of array locations. But it'll also save us some work with array locations. So we're always going to use a sentinel node, always for now. So we're going to have at least 1 node allocated. And we don't care what the data is, but sometimes it's useful to put a magic value in there, so that if you accidentally use the data field from that node, it jumps out at you. So that's why element 0, we're setting the data value to 42. Now if you write code to print out the data in your list, and you see the number 42 show up, you know that you're looking at the sentinel node's data, and that's a mistake. Or if you have a list containing 2, 3, 5, and you try to delete 42, and it says, okay, I succeeded, you know you did something wrong. Because you should never look at this data, you should never delete this node, right? The only thing you do with this is you change what it points to. And it points to the first data node. All right, let's take a 5-minute break and come back, we'll start talking about PA1.